Hello kids, today we'll learn about Josephson effect. Our friend electron with eyes will accompany us on our journey, and in the end there will be a squid. Our friend is roaming in the magical land of superconductors. It's their favorite picnic spot after all. To understand why, let us first understand the less magical land of conductors. While traveling through the land of the conductors, our goofy friend encounters numerous obstacles. This obstacle slows it down by offering resistance. This is famously captured in Ohm's law. However, when the conductors become cool, they change into what we call superconductors. This is where the magic happens. Superconductors offer zero resistance to our goofy electron. This means an electron, or more generally, a current once set up in the superconductor can be sustained till eternity. The temperature at which a conductor becomes superconductor is known as critical temperature. But why do superconductors have zero resistance, you may ask? Three dudes in 1957 tried to answer this question, and oh boy did they answer the question. According to their theory, an electron passing through the conductor attracts the positive charge ever so slightly. This temporarily increases the amount of positive charge at a location the first electron just passed from. The next electron sees this positive charge and rushes towards it. What we have achieved here is remarkable. An electron traveling through the conductor just modified the charges in such a way that to an outside observer it looks like the second electron was actually attracted to the first electron. This looks as if a negative charge just attracted another negative charge. Or, as a cool sounding physicist would say, the electrons formed a pair by exchanging a phonon. The cool physicist would then proceed to name these pairs Cooper pairs. The Cooper pairs can travel through the conductor without actually colliding with the obstacles. And no collision means no resistance. No resistance means superconductivity. Hooray! We have achieved superconductivity. The bond between the electrons in a Cooper pair is however weaker than the bond between a certain Glyn wolf and his 29 wives. Due to this, any Cooper pairs formed at a room temperature are broken by thermal energy of the arrangement of the positive charge, which is known as lattice. This explains why we need to cool the materials down to extremely low temperatures to achieve superconductivity. It is so that they do not accidentally break the bond between two electrons. There is one more idea we need to understand here, and that is the idea of quantum tunneling. Imagine our friend turning towards a wall. Under a normal circumstances, they will collide with the wall and get an express visit to emergency room. Pretty dumb. However, in the quantum world, our friend has a small chance that it can actually run right through the wall. Sure, it will lose some energy, but it will emerge out of the other side of the wall. This is what we know as tunneling. Okay, now that we understand the superconductivity, let us move on to the Josephson effect. Josephson effect is what we get when a bunch of Cooper pairs tunnel through a barrier sandwiched between two superconductors. This sets up a current through the barrier. The device thus formed is called Josephson Junction. The barrier can be made of an insulator, non-superconducting metal, or even thin connection of a superconductor. Josephson effect can be described by two equations that are obtained through a lot of
quantum mechanics.
But first, let us understand what is Josephson phase. The wave function of the electrons has different phases inside two superconducting ends of the Josephson junction. The difference between these phases is what we call Josephson phase. The heart of Josephson effect lies in the following two equations. The first equation gives the relationship between voltage across the Josephson junction and the Josephson phase, whereas the second equation gives the relationship between the current and the Josephson phase. There are two types of Josephson effect, AC Josephson effect and DC Josephson effect. AC effect is when a constant voltage is applied to Josephson junction. This causes the current in Josephson junction to oscillate with a known frequency. Similarly, in the DC Josephson effect, the current varies between the positive and negative critical currents. To summarize, the IV characteristic of the Josephson junction has a line corresponding to DC Josephson effect at V equal to 0 and large currents above the critical current. This is due to the normal tunneling of electrons through the barrier when the superconductor starts developing resistance. Now, coming to SQUIDs, superconducting quantum interference devices. A SQUID consists of two Josephson junctions on opposite side of square loop. A current is passed through the assembly which under normal circumstances would split equally among two branches of the loop. However, when a magnetic field is applied perpendicular to the loop, a screening current is formed which causes the current in one branch to increase and the current in other branch to decrease. This is SQUID's way to ensure that magnetic flux through the device is an integer multiple of flux quanta. It is possible to measure the magnetic flux by measuring the change in the current. Thus, SQUIDs have emerged as the best device to measure the astonishingly small magnetic fields. No electrons, squid, Superman, Superwoman or physicists were harmed in making of this video. This video is an extreme generalization of various concepts in physics that have perplexed scientists for centuries. All the scary mathematical equations and derivations were intentionally left out of this video. Please refer to the references provided with this video for more rigorous treatment.